Okay, so this is the second video for the second part of the structure of physics discussion. And we were talking about a motion diagram, and I was illustrating that for you. And we had gotten to this point when we needed to end the last video. And we had said that we have our frame of reference here, our origin and what direction positive x values are in. Then we have our initial x value, our final x value, our initial velocity, our final velocity, and then some velocity arrows to show the visual of the velocity. And then we have an unknown acceleration here. And now we said that we were going to take that information and put it in a slightly different form on the diagram here. We're going to create something called a given list. This means this is the information that's given to us. And so my initial x value is 0 meters. My final x value, I don't know. My initial velocity was 0 meters per second. My final velocity was 17 meters per second. By the way, you don't need to be writing this down. Just pay attention to the idea here. This is one of the tools that we're going to be using. So I just wanted to introduce this idea to you. You don't need to know anything about it right now. I just want you to see it. Okay? And then I'll say my acceleration equals question mark. And then let's say the time of the motion is going to be 4 seconds. So we went from 0 meters per second to 17 meters per second in 4 seconds. And we want to find out how far we went. So we need x. That's my final position there. We didn't have it, and we're going to try and figure it out. Now, you'll come to find out that we have a bunch of formulas that you'll eventually come to know and love that describe motion that we use for different situations. And in this situation, I have an initial position, I have an initial velocity, a final velocity, and I have time. And a formula that I could use for that to find position would be x equals x0 plus 1/2 v plus v0 times time. Okay, and all this is saying is that my final position, which is what I want, equals the initial position, which is 0, so that's going to drop out, plus 1/2 times the initial velocity plus the final velocity. So I'm just taking the average of my velocities, and then I'm multiplying that times time here. And then, again, you don't need to know these yet, so don't freak out, don't worry about it. And then I'm going to solve the problem. I'm going to say, oh, and by the way, my initial velocity there was 0, so that drops out too. So x equals 1/2 times v, which is 17 meters per second, times time, which is 4 seconds, and that's going to give me 34 meters. Okay, so this is how a motion diagram is going to help us. A motion diagram will collect all of the information for us so that we can see it right in front of our faces, and it'll do it in a way that it won't let us forget anything. Okay, so we'll go back to our presentation here. And we had said previously we're going to have a motion diagram and a vector diagram. You can see that typed out up in the notes here. There are also 3 main types of graphs that we're going to talk about, and we're just going to briefly mention these here. And so a graphical tool that we will use is called a position time graph. And then we're going to have one called a velocity time graph. And then we're going to have one called an acceleration time graph. And these graphs are just going to compare the relationship between position and how much time has elapsed where I'm at, in other words, in space, and how much time has elapsed, what the velocity is after how much time has elapsed, and what the acceleration is after how much time has elapsed. And these will be very confusing to begin with, but we'll get very good at them. Just wanted to show you what one of these things looks like. Since time is going to be the independent variable, right? It's going to be the thing that doesn't doesn't change in response to something else. It's the thing that something else changes in response to. So the longer the time, the difference in position. And so I have an origin on the left-hand side here. My origin is going to be my position. The thing that's going to bother us about this is that we're usually used to looking at the position of something, or how far something has gone, on an x-axis, and here it's on a y-axis. So to say that after 1 second, for example, I've gone 20 meters, and then after another second I've gone another 20 meters, and then after another second I've gone another 20 meters. The fact that these values would not be increasing on an x-axis is going to bother us, and we'll spend a great deal of time and effort trying to figure out how to use these graphs. And they'll be very useful to us, and you'll find out that there's an awful lot of math that you thought was worthless and a waste of time that in our circumstances is going to be very useful. So hopefully you'll look forward to seeing that happen. Okay, and you'll say, oh, that makes sense. I didn't realize that I would need that for this, and now I know that it was a good thing that I learned those things. So that's what you're going to say. Okay, so we're going to go on to the next slide. And so I want you to add these things to your diagram, okay? We've just talked about forces. Oh, no, we haven't talked about forces yet. We've just talked about position, displacement, velocity, and acceleration. We now are adding motion diagrams, vectors and vector diagrams, position time graphs, velocity time graphs, and acceleration time graphs to our diagram here. Okay, so add that, and I'm going to go ahead and move on. You can stop the video while you're adding that to your diagram. Okay, now that we've talked about motion, the next thing that we're going to talk about after we talk about motion is forces. And the study of forces, or the things that give rise to motion. Remember, forces give rise to motion. Okay, and that study is called dynamics. The study of forces is called the study of dynamics. You may be aware that the basic definition of a force is that it is a push or a pull. And for as significant of a concept as this is in all of physics, forces are like the major thing, right? As significant as this is, to say that a definition is as simple as it's a push or a pull, that may just be the evidence of how significant it is. It has such a simple definition. So with regard to forces, the main thing that we're going to want to know is, what is the relationship between the amount of force applied and the amount of motion resulting? And you don't have to be Newton to figure this out, right? You see this every day in your life. The greater the force, the greater the effect on motion. The greater the force, the greater the acceleration. That's what we're trying to determine here. If I use a certain amount of force, how much change of motion do I get? It should also make sense that how a certain force affects motion also depends on the mass of the object being pushed or pulled. The same force will have less effect on the motion of an object containing a greater mass. So in class, the example I have is I use a certain force to push a chair, and it accelerates a certain amount. And then if I use the same force to push the chair, but somebody's sitting in it, it's not going to accelerate as much. Okay, so that's the idea. The acceleration depends on the force and on the mass. And Newton formalized the relationship between force, mass, and motion by realizing that a net force, and in class I would have asked for some discussion about what a net force is. Here I'm just going to say that a net force is a combined or sum of forces. A combined or a sum of forces. Okay, it's a combined or sum of forces. And this causes an object to undergo acceleration, and the degree of acceleration also depends on the mass. Okay, so I'm going to go to a new blank slate here, and we're going to draw some things. And I want you to draw this on your diagram, or on your participation worksheet as well. There are spaces for this. And so the first thing we're going to say is, what was that relationship that Newton figured out? And we're going to say that acceleration is equal to the force divided by the mass. And again, what this is saying is that if I increase the force, because the force is in the numerator here, if I increase the force, let's say I multiply that force times 2, I'm also going to multiply the acceleration times 2, right? So if I multiply the force times 2, I'm going to multiply the acceleration times 2. I'm going to change it by twice as much. However, if I multiply the mass by 5 times, I'm going to slow the acceleration by a factor of 5. I'm going to divide that by 5 times. So if I multiply the force times 2 and divide the mass by 5, or increase the mass by 5 times, I'll have an acceleration that is 2/5 of the original acceleration. So let's put some numbers to that. Let's say that my force is 10 newtons and my mass is 10 kilograms. Okay, so 10 newtons divided by 10 kilograms equals 1 meter per second squared. And don't worry about the units right now. Don't worry about that at all. Now, let's suppose I double that force, and let's say I have 20 newtons of force, and now I have multiplied the mass times 5. Now I have a 50 kilogram mass. It's going to be a lot harder to push that, right? My acceleration is now going to be 0.4 meters per second squared. Okay, so that's the way that Newton characterized the relationship between acceleration and force and mass. Okay, now one other thing. He said that this requires a net force, and what we mean by a net force is, suppose I have an object here and it has a force of 10 newtons acting on it in one direction. That's an unbalanced force. There's no other force acting on it, and that kind of a force, an unbalanced force, is going to cause an acceleration. But what if I have a 10 newton force in the opposite direction? I'm going to have 10 newtons plus negative 10, and the overall or net force is 0 newtons. And since there is not a net force acting on this at all, there's a 0 net force, I would have a no acceleration. If I had another 10 newton force here, okay, then I would have more force to the right than I do to the left, and so I would accelerate again. But if I had another force in this direction that was 10 newtons, I would be balanced again. I would have a 0 newton net force. Okay, so we're running out of time for this video. Let's go ahead and stop this video. We're probably going to have to actually add a third part to this discussion rather than just ending it with 2. So we'll have a third video, but we're going to also end up having a third part to this. So I'm going to stop the video right now.